All right, welcome back, and we are going to start shortly. I had some issues right on the onset, so I think things are going to be fine during the stream. And as usual, raise your questions in the live chat. I shall be definitely answering your queries. All right. All right. So I believe you recall block diagrams, right, from our signals and systems classes, right? So whenever we draw something like this, which is like whenever we represent a system with something like a box, okay, this essentially becomes a part of what we call a block diagram, right? Of course, the name came from the fact that we are representing a system, a complete system, or rather parts of a system with blocks, right? So this is a very high level abstraction. So whenever I say a high level abstraction, you have to understand like this is something like a bird's eye view. So if you are looking at things from very high up, things will, I mean, very minute details and small details will be no longer, you won't be able to see them, right? So yes, so what we are doing, we are working at a high level abstraction. So what we are doing right now, we are kind of representing how the system interacts with inputs and outputs, right? So a very simple block diagram would have something like this. Again, so this completes a very simple block diagram, right? So where I am representing a system with a rectangular box, and then I have inputs to the system and outputs from the system, right? And of course, for our particular purpose, we are considering single input, single output systems. So all our systems do have one single input and one single output for each of them, right? So now here, this is the system. This is the system. So again, what we are saying is that we are abstracting everything at a very high level, which means how the system actually works inside, we are right now not concerned about that, right? We are simply concerned about the fact that we have a mathematical representation, or rather mathematical description, that tells me how the system interacts with input signals and generates the responses or the output signals. So that mathematical understanding, or that mathematical relationship is somehow known to us. Maybe we have derived it, or whatever it is, we know how the system interacts with qualifying input signals, also known as excitations, and with that interaction, how it generates output, right? So the input output relationship for that particular system is known to us, and that is what matters for me right now at this top level abstraction. So this is one of the highest level abstractions that you can actually do in control system engineering, and I'm using the term abstraction as a very generic term. Abstraction means whenever, say for example, if for example a very simple thing, for example, if a child asks you, okay, how so if a child asks you, for example, whenever we eat food, how that really works, how does that eating food actually gives us energy, right? If a child asks you that question, your answer would be pretty simple, right? Something like, say for example, this question is being asked to you by, say for example, a 5-year-old child, right? So you would say something like this: we eat food, and that is somehow burned inside our body, and that gives us energy, right? But if the same question is asked to you by a 10-year-old, you might give them a slightly better answer, right? We have a digestive system that digests the food, and from that we get energy, right? But if a medical student asks you the question, for example, someone who is trying to become a doctor, for example, then of course your answer would be slightly more complicated, right? Slightly deeper, right? So that way, a same question can be answered at different levels of abstraction, right? So rather different levels of simplicity, right? So here we are looking at a system at the top level abstraction, where I have a system, we have an input, and we have one output. So that is what we are going to do today. We are going to look at systems at top level abstractions, and we shall learn how to reduce the abstractions and pull them at the highest level of abstraction that's possible. So we're going to learn that, and we are going to do that in two different ways. So one of the ways that we are going to learn to reduce the abstraction is block diagram algebra, and the next one would be and this would be done in our next class. We would have signal flow graphs. These two are two different mathematical tools achieving the same purpose. So these two different mathematical tools have the same purpose of reducing abstractions in block diagrams, okay, in our system representation. And these two tackle the problem in two different ways, but they end up with the same result, right? So we shall do signal flow graph on the next class, right? Again, as usual, during the class, if you have any difficulty, just raise a question in the live chat. I shall be definitely answering your query, right? But this is fine so far as our systems are concerned, right? But we, by virtue of having studied signals and systems, right, we do know really that often the mathematical representation of a system could be represented, or rather can be represented, through something called a frequency response representation, right? Something like that. And here in this course in control system engineering, we shall switch out Fourier transform for Laplace transform. We shall see, just for the moment, right? So if I do something like that, if I represent the mathematical representation, the interaction between the input and output by means of the system, okay, then what we usually do, we represent the input by its, so this is the input as a time domain signal. So what we do, we apply some sort of a transform, namely we used Fourier transform to apply on the time domain signal, and that generated a frequency domain representation, right? So, and there is an advantage of representing everything in frequency domain, right? So if I represent the signal in frequency domain, so essentially x would be a Fourier transform of xt. Now again, I'm telling you once more that in this semester we are going to switch out Fourier transform for Laplace transform, in favor of Laplace transform, because there are certain advantages, simplifications that you would get with Laplace transforms. We shall see. But for the moment, I'm not writing omega. So if I do a Laplace transform, I would get something like x omega. Fourier transform, then I would get something like x omega. I'm not writing omega. If I get use Laplace transform, I would write something like this. So the frequency domain variable is going to be s. Again, I'm skipping that because the things that I'm going to teach you today are applicable both ways. If I apply Fourier transform, it's applicable perfectly. If I apply Laplace transform, then it is applicable perfectly, absolutely without any modification. That is why I'm just keeping the frequency representation. I'm just representing the transformed signal with capital X, or rather uppercase X, and then transformed output as uppercase Y, and the system has a frequency response description. And now we used to represent frequency response with H. Now for this particular course, because of standard control system nomenclature, we shall use the frequency response representation as G. Again, it could be G omega if you are thinking about applying Fourier transform, and it could be GS if I am applying Laplace transform. But I am just writing G to represent that it is independent of what kind of transform I am using, right? As long as this is true, right? You recall that I can under the frequency domain, I can calculate the output in frequency domain as the frequency response function, and this function is also known as the transfer function, and we shall discuss that at a later class with much better details. But this frequency response function is also known as the transfer function. Why is that so? We shall learn later on. But we have to recall something, that in the frequency domain, the output of a system can be calculated by multiplying the frequency response or the transfer function of the system with the Fourier transform or Laplace transform of the input itself. So that is something we already have known throughout our last semester, right? And that is why we really apply this kind of transforms, because the system's interaction with the input and the output, how it interacts with the input and generates an output, is often a differential equation, and solving a differential equation is much more difficult than solving an algebraic equation. So what this kind of transforms usually do for us, they convert differential equations into algebraic equations, and we actually derived all these expressions for us. But for the moment, imagine this to be something like a gain, right? So that's the idea. Whenever we convert a system representation from the time domain into the frequency domain, what we essentially have a complex gain. A gain is like an amplifier, right? So it's a complex gain. So what happens is that we have a complex input signal, and that gets multiplied with the complex gain, and that gives you the complex output, something like that. These are all complex numbers. And again, we are going to have certain recaps, but we are going to see those things, right? Now with that said, we essentially have three representations. Okay, but before I go into the representations, there is something I need to clear up right now. That if you look through any standard books, you might see a lot of descriptions, lot of formula for how to actually deal with block diagrams and things are given. Unfortunately for me, I cannot remember any formula. I can only derive things. But then again, the problem is, if I derive the formula for you, then what I am doing essentially, I am asking you to remember the formula, right? But if I am considering you people to be something like me, someone like me, in that case, you might also have difficulty understanding or remembering a huge set of formula, right? And remembering something blindly is not a good idea. It's never a good idea, right? Watch Three Idiots. So don't ever remember something blindly, right? Don't ever mug up anything blindly. So what we are essentially trying to do right now, I shall give you the framework, and right now in front of you, without even remembering any formula or recalling any formula from any book, I shall teach you how to figure out the formula by yourself. Okay, how to figure out the formula by yourself. Okay, so the block diagram reduction techniques would have different formula, right? And there are many online tutorials as well. They just give you all the formula and ask you to mug up, right? That's not a good idea. All right, so that aside, again, whatever I'm going to teach you right today is going to be absolutely self-sufficient if you understand everything, right? So if you understand this thing, you would be able to absolutely calculate everything, right? All right, without any issue whatsoever, without referring to any formula whatsoever, right? Because these formulas are not very difficult to derive. All right, so there are three fundamental structures in a basic control system, right? There are three fundamental structures. Let me just start with the most fundamental structure. Okay, so there are three fundamental structures. The number one fundamental structure is a cascade configuration. Right, so you have encountered cascade configuration in your signals and systems classes, and I recall vividly because I did teach you that subject, right? All right, and again, you have to understand something right here, that we have just jumped into frequency domain, right? And again, we shall have a lot of classes on Laplace transform like we had on Fourier transform, right? So yes, all your mathematical needs will be satisfied. So don't worry about that. I do not really like to teach mathematics without teaching you mathematics. Right? So the idea is that if the say for example the transfer function or the frequency response is g1 for this system, and for this system it is g2, then if x is the input here, then the output here would be, what was the output here? The output here would be, say, just for the moment assume the output to be z here, okay, and the output to be y here, right? With that said, let's go back. How did I define g? G was defined by the ratio of the output to the input in the frequency domain. And there are certain considerations. We are going to talk about that when we study transfer functions. But for the moment, that is what it is, right? So this can be derived simply from this equation, right? And we actually had discussed these things in our signals and systems classes with the perspective of signals, right? But for the most part, this is the ratio, right? So the output is essentially the input signal multiplied with the gain in the complex domain or the frequency domain, right? So that is simple, understood, right? So again, if you have any difficulty understanding this, feel free to ask, right? So right off the bat, if I ask you what was Z, then I'm saying Z is the intermediate signal. Understandably, what happens is, so this is the actual input to the system and this is the actual output from this cascaded configuration, right? And here x is going into the first system whose transfer function is g1, and of course the intermediate output that comes out of g1 would be z here. But what is z really? I can say z is nothing but x into g1, because that is how it behaves in the complex frequency domain, right? So that's going to be g1 into x. Pretty understandable, right? But if z is g1 into x, then let's look at y. But what is y? Y would be y is the output of system g2, right? Y is the output of system g2. Now of course the input of system g2 is z, so the output would be g2 into z. Of course g2 is the frequency response or transfer function or gain in complex domain, whatever you want to call it. So g2 into z, that's going to be the output, right? But again, question, what is z? I already know about z. What is z? Z is g1 into x. So if I write something like that, so I have g2 and instead of z I can write g1 and then x. So this is essentially g1 g2 x, because the order in which I multiply complex numbers do not matter. So essentially the output of the system was g1 g2 into x, right? So now with that knowledge, do tell me, can I say something like this? So instead of writing these two systems in cascade, can I say something like this? I have a single system whose input is x, whose output is y, but instead of the transfer function or the frequency response function or the complex gain, so let me just write these terms down. So we are considering g to be transfer function, or frequency response functions, or complex gains. If g is any one of these, it is going to be, or whatever we are going to derive today and also in our next class will be identical. Okay, so we get transfer functions if we apply Laplace transform, we get frequency response functions if we apply Fourier transform, and both of them are essentially complex gains. So yes, all these three nomenclature are kind of interchangeable. And don't worry, we're going to dive deeper into the mathematics of all those things, right? All right. So, so in the cascade configuration, so can I say something like this? So this and these two are equivalent. This and these two are equivalent. Why? Because very simple, you can understand, if X is the input to this system and Y is the output from this system, then of course Y is going to be G1, G2 into X, because G1, G2 is the transfer function for this system and input is X, so output is going to be Y, that is G1, G2 into X. Of course, very simple, right? This gets multiplied with the input, as simple as that. So this is the equivalence between a cascade configuration, right? So if you have two transfer functions cascaded, so that is something you can have. All right. And of course, by this, you can have a simple corollary that tells you something like this, that if I have a cascade configuration with many systems, like something like this, so now I have n number of systems where the input is once again X and the output is once again Y, but the transfer functions are G1, G2, G3 up to Gn. In that case, of course, the equivalent system would simply be represented by the product of the individual transfer functions. So essentially you can understand that the output here is G1x, the output here is going to be G1, G2x, and so on and so forth. So essentially what we have is an equivalent system that has a transfer function represented by the product of all the individual transfer functions. So that's a simple corollary that you can actually figure out from the original theorem that I just said. So this is cascade configuration. All right, no problem, right? I think. Okay. So if you have any query, I mean any difficulty, if you are feeling it that it might be difficult for you to understand, feel free to ask. All right, excuse me. All right, so before I go to the next configuration, let me explain a few blocks, particular blocks that are not just simple input-output blocks like that. Okay, so now we have some essential blocks, so extra. So this is kind of extra knowledge, right? You need to have this extra knowledge. So in our last class, you might recall that we you would recall that we introduced that standard nomenclature of the control system, right? Okay, standard nomenclature of control systems, and there we had a comparator block, right? We had a block that was something like this. We had a comparator block where we had a plus symbol here and a minus symbol here. Some sort of a signal was going in and some sort of a signal was going in from that. So for that particular scenario, this was the reference signal. Okay, so this was R and this was the feedback signal, so that was B, and this was being compared, so to say, right? So the reference signal, what I want, or rather what I wanted, was being subtracted from what I had. So the feedback signal that was coming from the sensors and those were subtracted, right? B were subtracted from R. So essentially out of this comparator block, the signal that I get as the output is not a multiplication of R and B, but a subtraction. Very simple to understand, I think. The signal that is generated out of these is basically R minus B, and the plus and minus symbols, these are actually pretty self-explanatory. All right. All right, so this is one of the comparator blocks. So this is the comparator block, we call it a comparator. Okay, right, it's a comparator block. Similarly, I can have a plus sign here as well. In that case, these two signals are actually summed up. The output is basically a sum of R and B. This could happen, okay, depending on what I want. So this, in this scenario, it's called a summing block. And in fact, since you have studied analog electronics, you know that creating this kind of blocks using analog components like op-amps is not a difficult task at all, right? Creating summing blocks, creating comparator blocks, and such is not a difficult task at all using op-amps, right? So this is called a summing block. Now, summing blocks can be even slightly more involved like that. For example, this is also a summing block. Imagine again, the arrows are pretty important here. The arrows pretty much denote in which direction the signal is flowing, right? So say this is X, this signal is Y, this signal is Z. Of course, the output of this summing block would be X plus Y plus Z. So this is again another summing block, right? Right. The summation could happen from the top only, right? So it could happen that I have this signal coming up from here, this signal coming up from here, and there is no signal here. So it's very simple to understand, right? I believe. Again, this comparator block could have this representation. But I'm just saying these things because anyway, in any case, these things are pretty self-explanatory, but still I'm explaining these things so that you don't have any doubt later on. Okay, let me just draw it once again because I messed up. So I can have a comparator that kind of looks like this. So B is coming from top. Again, this is just like a circuit representation, right? Whether it is actually coming from the top of another signal, I mean, that makes no sense, right? So what we are doing is an abstract description of the system, right? So this is again the same thing, R minus B. So again, if you have any difficulty, feel free to ask. This is again another comparator. Right. I think these things are understood, right? You could have multiple signals like that. So I could have another minus sign here. Okay. Someone is saying, yes, what if I have more than 3 signals and such and such? So for example, what if I have 10 signals? How am I going to represent that here? Yes, that's a very fantastic question, right? So in general, so this is called a summation block. In general, what you essentially do, you draw the block as a vertical rectangle. You put a summation symbol here, and then for example something like this. So this is your x1 signal. Say I'm just considering 5 inputs. Right? So these 5 signals are coming up, and some of them are being subtracted, some of them are being added, say. I think this is self-explanatory. The output that is generated by out of these is x1 minus x2 minus x3 plus x4 plus x5. And in fact, you shall learn during this course at a certain some point how to actually construct these kind of blocks, because you will be required to actually construct this kind of blocks. So if you have more than 3 inputs, this is the way to go. And this is pretty self-explanatory, right? No, someone is asking, does the left sign always have to be plus? Say, just to avoid any confusion like that, let's say we have something like this. I think I answered your question. All right. So in general, that is how we represent a summing block, right? And I'm not saying that you are not going to encounter this kind of signals. You are going to encounter this kind of things, but at a later point of time, and you shall actually learn how to use op-amps to construct this kind of circuits, operational amplifiers, right? And we shall have a small class on op-amps as well, because I assume that you won't be able to recall anything from your analog electronics classes, because that's pretty much usual with you people, right? So I think we have completed our discussion on the extra bit on how comparators are symbolically represented, right? Again, we are not going into the, try to understand once again, we are not going into the details of how these blocks are constructed, right? What kind of electronic components there are inside these blocks. We are not interested about that, right? We're just interested about how it interacts with signals, interacts with input signals, and how it generates its output, right? So that is what we are interested about. So that is why we are saying we are looking at a high level abstraction, right? That's understood, I believe, right? So with that said, let's move into our second type of configuration. So we talked about cascade configuration. Now let's talk about something called the parallel configuration. And just before you, you might ask, where is series configuration? There is no series configuration. Okay, so this is parallel configuration. So for example, in parallel configuration, what happens? You have one input signal that comes out of something, I don't know, and that is branched like that, and two different systems are fed with that same input signal. So I essentially have G1 and G2 receiving the same input signal X, and their outputs are something like summed up by a summing block, and this is the output. So this is Y. All right. So again, if you are drawing a block diagram, or if you are doing anything in control system, if you are drawing anything, if you don't put the arrows, then your drawing is incorrect, pretty much. Okay, signals will flow in one direction, right? So you have to put the direction properly, right? And some people like to put an arrow here as well. Yeah, I don't, but some people do, right? But yeah, in some books you might see an arrow here, but I don't. Anyway, so what signal is received by this system? Yeah, signal X is received by this system. What is the output of this system? Of course, it is G1X. Again, what signal is received by this system? That's X again. Output is G2X. And this is actually summing the two signals. So it is summing G1X with G2X. So what is the output essentially? The output is essentially G1X plus G2X, right? So this signal is G1X and this signal is G2X, and these two are being summed up by this summing block. So the output is going to be G1X plus G2X, right? So but out of these, I can simply take X, factor out X. So I can say this is like this, G1 plus G2 into X. I can factor out X like that, and I have something like this. So essentially the output is equal to G1 plus G2 into X. So essentially what I can say, instead of having this cascade, this parallel configuration, I can have a single system whose transfer function is G1 plus G2, and the inputs are as usual X and Y. Because for this system as well, the output is going to be as usual, it's going to be G1 plus G2, and that's going to be multiplied by X, because these two are identical. So we have an equivalent representation again. So this might give you that circuit theory vibes where you actually studied how to reduce circuits, right? Simplify circuits. This is somewhat like that. This is very much like circuit simplification. right? All right. Okay, someone has a very interesting question. Yes, someone is asking that, okay, when I'm dividing the signal into these two branches, will not the strength of the signal get reduced and all? The answer is absolutely yes. The strength of this signal will automatically reduce if I divide it, if I tap two signals from out of one branch, right? That happens, right? But we are considering a situation where there is no loading effect. Okay, we are considering a situation where there is no loading effect, which means that this system will be drawing zero current out of this, and this system will be drawing zero current out of this. Okay, and we shall explain what I mean by loading effect and everything. So again, just to be very clear here, we are considering ideal situations. In a non-ideal situation, if these are all analog signals and if I divide something like that, what happens is the signals will be branched out and the voltage will automatically reduce and all, right? But again, try to understand, we are not feeding power here. This signal X is not feeding power to this, right? If you recall our earlier classes, we had a power system in addition to the entire signal transmission, right? So this system and this system, they are being fed with power in addition to these signals. These are signals. These are not giving this G1, G2, these systems with power. This signal X is not powering this these systems, right? So we have additional power systems associated with our control system that actually is responsible for powering up the circuit, right? All right. So yes, so even if I divide these signals, it won't matter as long as this system can understand that this is that X dash signal, it is still going to be fine. Do you understand? Because this is not responsible for powering up the circuit, right? For power, we have additional systems, right? And again, we have something called a zero loading effect. Again, everything we are discussing right now is kind of mostly in theory, right? And we shall give you practical examples where things will violate, I mean, slightly deviate from our standard theory, right? But here we are considering ideal situations, right? That's the thing, we are considering ideal situations, and I shall show you how things differ from ideal situation and how you can reduce the loading effect so much that pretty much things behave like ideal circuits. Okay, and again, in order to reduce loading effect, you require something called op amps once again. So op amps are pretty much the fundamental building blocks of analog circuits, analog electronic circuits. All right, so we're going to use op amps to actually construct this kind of configurations, right? Again, these are not just your run-of-the-mill electrical circuits, right? This kind of mathematics won't work with your standard electrical circuits, right? We need to reduce the loading effect to zero, and for that we would need something called buffers. Buffers are created through op amps. We need this kind of things. All right. So with that said, this is understood, right? And this is again, I can again say the same thing like this. Say for example, I can divide this into many different and so on, right? So say this is G1, this is G2, and this is Gn. So this is X, and of course there are plenty of signals coming out. And there is just one more thing. If everything is summed up, then I can just put a summation like that, and I can pull in signals like that, right? So the output is of course G1x plus G2x plus G3x plus up to Gnx, right? So of course output is going to be Y, which is equal to G1 plus G2 and so on up to Gnx. So of course the equivalent circuit would be a sum of all these, right? So the equivalent would be G1 plus G2 plus G3 and so on, right? So the equivalent circuit would be someone is asking something. All right, so that's pretty simple, I think. All right, again, if you have any difficulty, try to tell me. With that said, let's move on and let's go to the third possible configuration that we could have. Okay, so we discussed our cascade configuration, right? We discussed our parallel configuration, and the third one is the most important one here. Okay, it's the feedback configuration. Okay, so we are just right now going to create a very simple feedback loop. Okay, again, in a very simple feedback loop, what you essentially have a system. Okay, now of course you would recall, let me just explain the way we did. You would have a controller. Okay, we would have a controller like whose transfer function would be G1, that would be controlling a certain system whose transfer function is going to be G2, right? And the output of the controlled system, so this is the controlled system. Okay, the output of that is represented through C, because that's called the controlled variable. Okay, that was being measured by certain feedback elements. Specifically here, we would have sensors, transducers, and everything. So we would have a block called H. So these are the feedback elements block, and I would have a reference input signal, if you recall our last class. And reference is what I want. Okay, and this is what I have, right? So we are comparing what I want with what I have, and based on that, I am trying to figure out, or rather the controller is trying to figure out whether to increase the input, increase the manipulated variable or not, right? And this is the actuating error signal, right? So this signal is known as the actuating error signal, this signal is known as the manipulated variable, this signal is the feedback signal, and of course this is the controlled variable, right? We discussed the nomenclature in our earlier classes, right? So this is a standard feedback config, right? A very simple feedback configuration, right? Now, right at the beginning, okay, again, just one more thing, and I need to simplify this a little bit. Okay, so right on the onset, you can see that system G1 and system G2 themselves are in a cascade configuration. These two themselves are in a cascade configuration. So I could combine these two into a cascade, equivalent cascade block, right? So I can combine these two into an equivalent cascade block, and that is what I'm going to do right now. Because these two are just right next to each other, and the output of G1 is actually going as the input of G2, right? So I can combine these two as a single block through the cascade mechanism. And there, let me just show you. There, what I can do, I can get rid of all these two blocks, and I can instead have a single block that was equivalent to having these two blocks, right? The controller, this is the controller, this is the system, rather this is the control elements, the controlled system, this is the feedback system, rather feedback elements or sensor elements, whatever you want to call it, reference input, feedback signal, controlled output, manipulated variable, and actuating error signal, right? So of course, by the equivalence of in cascade configuration, you know that this is going to be G1 G2, right? G1 G2, that's going to be G1 G2, right? You know that, right? Because the output of G1 is going as the input of G2, right? That's understandable. But for my sake, let me just reduce this circuit even further. Okay, let me even make this even smaller and more simpler by saying that all right, we have the same configuration here, but instead of calling it G1 G2, Because try to understand, g1 is a complex function, g2 is a complex function. I can of course multiply them, and if I multiply them, I can also call them with a different name, right? So what I have essentially done, I have clobbered g1 and g2 together, and I am now calling them just g. Right. And I'm giving the standard nomenclature once more here. Okay, I'm considering the input to be x. Instead of calling the input to be r, I'm just calling the input to be x, and the output to be y instead of calling it c. But you have to, in your mind, remember that these two are identical. These two are again identical, and g is essentially g1, g2, right? So this is what is known as a simple feedback loop. This is what is known as a simple negative feedback loop. This is what is essentially known as a simple negative feedback loop. Now, what am I actually doing with this negative feedback loop? What I am doing is that, of course, I am measuring the output of the system, and based on that measurement, I am comparing with the reference, like we did have an elaborate discussion in the last class, right? So we are measuring the output and comparing it with the input, and we are generating the actuating error signal E. That remains here. All right. But notice the term negative feedback, and we shall quickly learn why negative feedbacks are important in control system. Okay. Positive feedbacks are not really, right? So try to understand something. Okay, you want to improve yourself, right? You want to improve yourself. So which one is better for you? Negative feedbacks or positive feedbacks? Okay. So if you have constructive negative feedbacks, say if someone tells you, okay, these are the places where you are doing it wrong, you have to improve, right? So constructive negative feedbacks are better for your life and better for your control systems as well, right? Imagine you are a student, right? And every time you are making a mistake, I'm still telling you that, okay, you have done nice, fantastic. What will happen? Your performance will gradually decline, right? Because you are getting a pat on your back whenever you are even if you are doing something wrong, right? That's not how life really works. Okay, your quality of life and your life choices will automatically improve. What you are doing in your life will improve if you get constructive negative feedbacks. So what are constructive negative feedbacks? Constructive negative feedbacks are those feedbacks that criticize you for your shortcomings, but in a constructive way that also helps you to build up to reduce those errors. So here the purpose of the entire system is to reduce the error signal to 0. So that the purpose of this entire control system is to reduce the error signal to 0. And what is this error signal? Error signal is the difference between what I have, difference between what I want and what I have. I want X, but I have Y. What is the difference? Okay, the difference is basically E for that matter, right? So this negative feedback actually lets you reduce the feedback, essentially like the previous car example that I told you. I was traveling at 40 km per hour, but I would want to travel at 60 km per hour. So I have a 20 km per hour deficit, right? So that negative feedback told me how much I have to improve, or rather how much I had to improve, right? But under ideal scenario, when I am exactly achieved my goal, so what I want is what I have, then essentially the error signal is going to be 0 for that matter. And with that, when the error signal is kind of like 0 or something like that, then I would say that, okay, fine, I have now reached my goal in a sense. But that could never happen if I only have positive feedbacks, right? So in life also, positive feedbacks will make you feel better, but will never let you improve yourself. Yes, positive feedbacks are good for our life so that we feel better, right? But negative feedbacks are essential for us for growing up, really. But constructing negative feedbacks, like you cannot just thrash people right and left. You cannot do that. But constructing negative feedbacks are good. And these are essential, absolutely essential in control systems, right? These do not have feelings, right? but they do understand mathematics. So everything in the universe is governed by mathematics, right? So these systems do not have feelings. So if you give them negative feedbacks, their feelings won't be hurt, but their workings will become better. And positive feedback, technically in our control system, we shall learn later on, positive feedbacks make system unstable. So if you want to destabilize something, constantly give them positive feedback. They will automatically degrade their quality and they will become unstable. Really, that happens in real life as well. So life lesson, TDG's life lesson, right? Anyway, so let's go with this and try to understand the mathematics here once again. So this is y. Again, this was y. Again, we have just changed the nomenclature slightly. So instead of calling it r, I am calling it x. Instead of calling it c, I am calling it y. And in many books, you might see x, you might see y. So x, y, you might see r, c. Doesn't matter, as long as you understand the mathematics, it does not really matter, right? So y is being fed to this system. Now we just have changed the direction from which the signal is coming to. Someone is saying, in this case we are getting the output even if there is a major error. We will only get the output when error is zero. So yes, the point is okay. We shall discuss the errors we shall have a class on errors. So don't worry about that. So if you have any query about errors, so you can rest assured that those queries will be resolved in our class on errors. We shall have a class on errors and sensitivity. Hold on a second. It just started raining. Hold on. All right. So now look very carefully here. Is that y is going into this system H, right? Okay, hold on once more. Oh, sorry. Okay, let's continue. All right. So, and here is a nice problem that I encounter. Whenever there are, even if there is a small rainfall, my internet connection is going to go down. Usually goes down. Okay, I hope that doesn't happen today. So the output is going to be hy, right? So h is the transfer function here, y is the input here, and output is going to be hy, right? So question is, what is e then? What is e? So e is the comparison between x and hy, right? So hy, so x minus hy would be e, right? So that's going to be x minus hy. Right? So that's going to be e. But what is y? What is the output? But what is the output? Output y is essentially e into g, because e is the input to this system and y is the output of this system. So y is essentially e into g, right? So g into e, I'm saying that. So essentially we have another formula, say y equal to g into e. All right, right? So with that said, from this equation I have y equal to g into e, but instead of saying e, instead of writing e, I can replace e with this one, x minus hy, right? And now I can simplify this even further. I can say y is equal to gx minus ghy, right? And I'm just pulling this to the left hand side. So I have y plus ghy is equal to gx, and there I can factor out y. So I would have 1 plus gh, and then I would have y, and that would be gx. And now I can do something like a I can pull this x down in the denominator of y, and I can pull this term down in the denominator of g. So I can have y by x equal to g by 1 plus gh. So what is y by x? Y by x is the equivalent transfer function between this input and this output, right? So y by x is the equivalent transfer function between this input and this output. So let me just copy the drawing here once more. So right now, this was the system, right? And let's forget all the intermediate signals here, right? So if I want to construct, construct an equivalent system, right, that has this x as the input, and this is the equivalent transfer function, and it has this y as the output, then the equivalent transfer function is going to be this ratio of the output to the input, something like this. So this is going to be the equivalent transfer function, g by 1 plus gh. So that's going to be the equivalent transfer function. So this is the equivalent transfer function for a negative feedback loop, right? So what we are saying, we are considering feedback config, so rather a negative feedback. All right. So as your homework, you would have to construct the positive feedback scenario. So in a positive feedback scenario, you would have something like this. So this is going to be your homework. So in the positive feedback scenario, this is going to be plus, of course. This is going to be plus, and you have to construct the equivalent transfer function. Okay, you have to construct the equivalent transfer function exactly the way we did it. Okay, so homework would be a positive feedback. And later on, we shall prove that in 99% of the cases, positive feedback would destabilize the system, make a stable system turn into an unstable one. And for this one, you have to prove that the equivalent transfer function for positive feedback is this one. You try to prove that, right? All right. So with that aside, we have pretty much taken 1 hour and constructed all the fundamental structures here, right? All the fundamental structures here, right? So this is the fundamental building, these are the fundamental building blocks of what we call the block diagram algebra. So whatever we have done so far is nothing but algebra, and we have used algebra to reduce our block diagram into single blocks. Try to understand one thing one very crucial thing here, that throughout this, whatever we are learning so far, throughout this, what we have done, throughout this, whatever we have done was to reduce the block diagrams into a single block. So we are just lifting the level of abstraction so that we are only seeing the input and the output, and everything that is happening inside, even these small details like that, are being clobbered into a single block. So that is what we have been doing so far, right? See, so everything is getting reduced to a single block. So that is what we are going to do in this block diagram algebra. So block diagram algebra is essentially an algebra, or a certain part of algebra where we take complicated block diagrams and reduce them to a single block, simplify them into a single block, so that we get a concrete relationship between the input and output, right? So we will do that. So again, the rain has stopped, so please wait for a while. All right. Sorry for the intermittent disturbances. All right. So let me just do something. So now big examples. Nice. Nice. Right. Just like I gave you sample a question bank on signals and systems, I similarly also have a question bank on control system as well. So it is just a copy from that. Right. So now I have just taught you very simple things, and we shall now try to figure out from that very simple idea how we actually solve this entire complicated block diagram and figure out the transfer functions per se, right? So figure out the whole transfer function, right? So for our particular purpose here, we are just going to not consider this S here. Forget the S, because this is also going to work for Fourier transform, other integral transforms as well, right? So R is the input and C is the output, right? Okay, let's even forget that. Let's forget these. Let's forget these. Let's consider this to be X and this to be Y, right? So now I have two blocks like this. So I have G1, I have G2 here. All right. Okay, this way. I won't write S. So that is something you have to remember, right? So I have these two feed forward blocks, and we have two feedback blocks. So I have one H1 feedback block, which is taking the signal out of this and pulling it back here, and we have another feedback block that is pulling the signal out of this and feeding it back here. And we have another feedback loop where we essentially don't have a transfer function here, but we are going to tell you how to actually treat that. Right. With that said, let's try to figure out how we can actually reduce the block diagram, right? So now try to understand a few things very easily. So we have a feedback loop here. Try to understand. We have a feedback loop here. But if we clobber everything together as a feedback loop, unfortunately what would happen? All these intermediate signals will be lost. All these intermediate signals will be lost, right? So there is one important point you need to remember, is that when we constructed the equivalent system here, all these intermediate signals were lost essentially. So if I now ask you in this equivalent block diagram, where is E? You don't have E. Where is B? You don't even have B. You just have X and Y. So all the intermediate signals get lost when we clobber everything together into a single equivalent block. So that is one of the things that you actually pay by reducing the complexity in the analysis, right? So with that said, I cannot consider that. Very simple thing. These two also, similarly, these two might feel like a feed forward block, right? Or like a cascade block, right? G1 is cascaded with G2. It might feel like that, but unfortunately, if we just clobber these two together, we once again have the same problem. This comparator block gets lost the moment we combine these two, right? So we cannot do that either, right? We have a feedback block here as well, but the same unfortunate thing would happen. Everything in between would be lost, right? Understood? And there is a problem, very simple. If I consider this to be a feed forward block, then this block gets lost. Then question remains, where would this signal go? Where would this one go? This one would have no place to go to, right? this signal would have nowhere to go. So we cannot let these kind of things happen, right? You understand what I'm saying, right? So if you combine these two as a cascade block, then this will be lost, and this signal that is coming from the H2 block will have no place to go, right? Will have nowhere to go. So we cannot let that happen. We can only let those things happen that will not affect others, that in a what should I say, a non-reversible way, right? All right, that's understood, I think. All right, so with that said, let me go through the trouble of drawing this entire thing, because that is the amount of trouble you are going to have. Drawing everything is going to be the biggest trouble in this course, unfortunately. I'm sorry, what question are you asking? Why is the arrow on H2 indicates both sides? Sorry, I don't get your question. H2 here, look very carefully. What it is doing, what H2 is doing essentially is that it is receiving signal from the output of G3. So the output of G3 is going into H2, and whatever comes out of that, and what comes out of that, H2 into Y, that goes into the comparator block here, if that answers your question. So there are no two directions. So actually this arrow is in this direction, because this Y is essentially the output of this system G3. That is what it is. Right. Let me just draw everything. Again, if you feel any difficulty, raise a question. Hold on, because drawing these things is the most difficult, or the most challenging task, really. So in the question bank, I have actually collected plenty of fantastic questions. Go through that. I will send that to you. So if you solve those problems, it will be very easy for you to cope up with the things. It will help you understand everything better. All right. All right. So if you have any query, so here this signal Y is being generated by G3 block, but this is being fed back by two points here. So this is being taken by this H2 system and being fed back here, and this is again directly being fed back here. So this is X. Now the most interesting point is that I would take this diagram and simplify this so often that if you are just drawing this in your copy, you won't be able to keep up with me, unfortunately, because it is essentially, for me, is like a blackboard, right? I can copy paste, no, not I can copy paste, but I can erase things as needed, right? So essentially, along with what advantages we have on a blackboard or a whiteboard, I can erase things. We have another advantage here. I can copy paste things, right? Yeah, I mean, being able to draw block diagram takes a little bit of effort. All right. So this is the diagram, right? So now I haven't told you how to deal with these things, right? Because I won't. But I have taught you how to actually think about it, right? So essentially what I see, try to understand, try to figure out situations like this. So if I consider this to be a cascade block and reduce this, this will be lost. Problem, right? That's a problem, real problem, right? But the thing is, what about this one? These two are also in cascade. Can you see that? These two are also in cascade, right? But if I combine them into a cascade block, if I combine them into a cascade block, again, simply because these videos will be there on YouTube for the foreseeable future, so I would request you to follow along. Don't be on a haste to copy everything in your notebook. Just try to follow along, okay? Right? Try to understand first and then copy paste if you want. And again, the handouts will be given to you in any case. Someone is saying G2 and G3 and H2 are in cascade. No. G3 and H2 are not in cascade, because what happens is a feedback loop. Try to understand. That's a feedback loop. It is not a cascade. The output of this somehow goes back into the input. So that's a feedback loop. Okay, so it feeds the output back to the input. So G3 and H2 are not in a cascade, but they are in a feedback. So the output of this is being fed back by H2 into the input somehow. That's a feedback loop. That's not a cascade, right? You get that, right? So now look very carefully, what thing I can change. For example, if I consider G2, G3 to be in cascade, then I have a problem. Problem is that I am going to somehow get rid of this point. This point would be lost, right? Somehow this point is going to be lost. All right, this point is going to be lost. So if this is lost, then so somehow, say, try to understand, if I combine these two blocks into G1, G2, G3, like a cascade block, then what happens? I mean, this signal that is coming into H2, H1 and going back to this signal will have no place from which is going to come out from, right? Why would it come out from? Because if I combine these two into a single block, this point is going to be lost. So this point is going to be lost, right? If I combine G2 and G3 as a cascade block, then this point would be lost. And if this point is lost, then why would this signal come from? So we would have a dangling point. So end of story. So I cannot do that. The question is, what can I do? So imagine an ideal world where this point was not even there. So imagine a situation where this wasn't there. Imagine a situation where this wasn't there, but this was somewhere else. This was somewhere else. Maybe this was, what about this situation? What about the situation where actually this came from here? Let me just reduce the drawing in a way that, right? What about instead of coming from this, what if this signal was actually coming out of this? Could we then actually simplify this? Question is, could we then simplify this? The answer is yes, because there is no problem right now with that. Because if this signal was coming from this, then this is a perfect cascade with no intermediate taps or anything, right? The same thing would have happened if instead of, so we are just imagining, right? There is nothing bad in imagining good things in our life. So instead of this signal coming out of this, if this signal was coming out of this, then I still would have no problem, right? Because there was nothing being tapped out of this. I could have just cascaded these two, right? I could have just cascaded these two without any issue, right? Right. Happy? Happy. Now I can choose any one of these. I could choose any one of these, and right now I will just ask you to vote. Okay, should I choose this option? And later on, when you are actually experienced enough, you will see which one of the options is better, right? So this is my option 1, say, rather this is my option 2, where I imagine that this was being pulled out of this. Okay, this is my option 2, and say this is my option 1. Now please vote which option should I choose. This is my option 1, where I pull the signal out of this. Please vote which option I need to choose, because it is going to be up to what you want. This is option 2. Option 1 is I'm pulling the signal out of this, imagining that I'm pulling the signal out of this. Option 2 would be I'm imagining that I'm pulling the signal out of this. So which option should I go for? Please vote quickly, do it very quickly. So I'm kind of waiting for your vote. Unfortunately, no one is saying anything. Well, is it that you don't understand something? Yeah, I'm not asking you to figure out what happens. Just vote for one of the options. I'm here to let you figure out what is happening. Just choose one option. So we have bigger vote on option 2. Right? The point is, I shall do both option 1 and option 2. Right? So first with option 1. Right? Let's first do option 1, and you will understand what I'm saying. And again, just before I even do anything, option 2 is a better choice here, and I'm going to tell you why. But both of them are the feasible options here. Let me just try to draw the block in a bigger way. Right. Someone is saying none, right? All right. Okay. Since many of you are overwhelmingly saying option 2, I'm going to deal with option 2 later on. Okay. After I tell you about option 1. So what if I imagine that this signal was being brought out of this, right? Right. Now let's go back to the original drawing, and let me get rid of these. Get rid of these. Right. Now, for our purpose, imagine the signal that was coming out of this was, say for example, who knows, A, maybe A. I'm calling this signal A, right? This signal A was coming out of this. So what was the output of this block? So what was the output of this block? Try to understand what is the output of this block. So of course H1 A, right? So if this signal is A, then the output of this block is H1A, right? But now if this is A, then this was the output of this block. Then what was the input here? If this output is A, then the input here must have been, try to understand that whatever was here, that got multiplied with G2 and gave me A. So this signal here must have been A by G2. Can you understand that? This signal must have been A by G2. Because unless this signal is A by G2, it cannot get multiplied with G2 and become A, right? This signal was A by G2. Right? That is understood, right? I don't think there is any problem, right? So if this is A, I'm just naming it for my purpose. And this is A by G2. And of course A by G2 gets multiplied with G2. That's how I get A. And of course since this is A, the output of this block is H1A. Right? So pretty simple. Output of this block is H1A. But now in my drawing, look very carefully now. Okay, what was this signal? This signal was A, right? What was this signal? This signal was A by G2. This signal was A by G2. Right? Right. So what is this one receiving? It is receiving A by G2. What was the transfer function? H1. So it was H1. What is the output? Unfortunately, the output is now H1A by G2. Right? Because this signal is A by G2. So A by G2 is feeding into this one. So the output is H1A by G2. Unfortunately, that is not what I want. Right? The output of this should have been H1A, not something like H1A by G2, right? The output of this should have been H1A, but instead I have H1A by G2. I need to take care of that. Point is, I need to take care of that. How can I turn this signal into H1A? I can turn this signal into H1A by writing a G2 here. If I write a G2 here, then try to understand that H1 G2 gets multiplied with A by G2 and gives me H1A. Now, no longer the input-output relationship is violated. I have A here and A by G2 here. I still have A here, A by G2 here. Now I have manipulated the transfer function here in a way that the output of this is still H1A. Right? The output of this is still H1A. Right? Try to understand, no input-output relationship has been violated anymore. Right? So instead of pulling the signal out of this, if I pull the signal out of this, then I have to manipulate this transfer function into H1 G2, so that none of the input-output relationship is violated. I have not violated or changed any signals. So the point in block diagram algebra is that you cannot change signals. You can change systems so that the signals do not change. Right? Signals are inherent properties of nature, for example, and signals are your environment, and systems are those that you have created. So you can change your creation, you cannot change your environment per se. So you cannot modify the signals. If you modify the system, you have to modify the systems in a way that your signals do not get modified. Your signals should not change. So I haven't changed the signals. So this signal was A, this is still A. This signal was A by G2, this is still A by G2. And this signal was H1A, this signal is still H1A. So I have modified the system in such a way that the signals did not change. So in block diagram algebra, the idea is that I can modify my system so that the signals do not change. And a similar but a reverse idea would be applicable in signal flow graphs. Like, feel free to ask me if you have any query, because you should have some queries, right, at this point. Right? Again, just keep in mind that we haven't somehow made up a signal A by G2, right? But this was there already, right? A by G2 is not a made up signal, it was already there in the signal system, right? Right. So is that understood now? I'm patiently waiting for your answer, because the point is I would proceed only if you understood this. Now, yes, we can multiply and divide as per our convenience. As long as the systems are ideal in nature, nothing can go wrong. Right. As long as we are not changing the signals themselves, we are just fine. Right? We are not violating physics here. We are not changing physics here, right? So as long as we are not modifying the signals, it's fine. Right? Now you can see, you can now treat this as a cascade, because the dependency that I was pulling out some signal out of this is no longer there. Now I can consider this to be a single cascade, because I am no longer pulling the signal out of this, right? I can now consider this to be a cascade, right? All right, so let's copy and pasta this one, right? So now I'm considering this to be my cascade block, right? So I can now consider this to be the cascaded block. So now here I'm just cascading these two, right? Right? So in this step I'm cascading these two. So G2 is in cascade with G3. Yes, H and G are different, but as long as I'm not violating the mathematics here, as you can understand that no signals are changing, right? They can be very different. They can be very different systems. Because our ultimate goal is to figure out the overall transfer function between input and output. And the input is X and output is Y. Right, all right. So again, feel free to ask. So G2 and G3 are in cascade. So I'm now changing them in, to an equivalent block where they are just. Again, don't think about how they are constructed, how H1 is constructed, how H2 is constructed, how G1, G2 are constructed. Don't think about that. Okay, just then think about them as complex gains. Okay, don't think about how they are constructed. And this is going to be nothing changed. Because see, the entire algebra was based on the fact that I'm not changing the signal. I cannot change the signals. I can manipulate the systems in a way that the signals remain intact. And this is how you also did your circuit theory classes, right? In circuit theory, if you reduce a circuit, you cannot change the currents and voltages, right? You can change the elements in a way that the currents and voltages throughout the circuit remain the same, right? All right, that is understood. But I told you earlier, but because your option was not a better option, or was not a good option. Option 2 was a good option actually. Okay, right? Option 2 was a good option, because right now what you see is that I kind of have a feedback loop. Look, see, I have a feedback loop like this one. this signal is coming out of this, going in through a system and being fed back. I have a kind of have a feedback loop. Unfortunately, there is one point in my way of the feedback loop, right? So if I construct the feedback loop like that, if I reduce the feedback loop into one single system, then I unfortunately would lose this point, right? So this system will no longer be able to tap this signal out. This system will no longer be able to tap this signal out. So now I don't have any other option but to choose option 2. What was option 2? Option 2 was to actually pull this side, this point back to this one. So we could have done that earlier. Now since we haven't done that earlier, now I'm doing it right now. So that is why I said I'm going to choose both options. But you could, right at the beginning, you could have chosen to put this on this hand, this side, and accordingly do the manipulation. You would end up with the same results, right? Figure that out. Right. So what we are doing right now is that let's get rid of these, right? Right. Get rid of these, right? Now let me copy and paste this. So now we are considering. So now what I'm considering putting this one here, right? Right. I'm considering putting this one here, right? All right. See, try to understand. We are going to apply the same mathematics here. Now, imagine in the original one. Now let's forget what happened earlier because we kept the equivalence between. Equivalence between these two, right? Okay, I made a mistake. What kind of mistake? I pulled this figure so far up that. All right, that's fine. All right, so now, so these two are equivalent, right? These two are equivalent. So let's forget about how we figured out about them. Now, once again, consider the signal that appears here to be A, or rather in this figure. So now we are figuring out an equivalence between these two, right? Considering the signal that appeared here to be A. Now imagine that, right? Then what would be the signal here? What would be the signal here? That would be G2, G3A. That would be G2, G3A, right? And what would be the output here? H1A, obviously. Sorry. Now, if this is A, then output would be H1, G2A. Try to understand. Okay. Right? Or rather, instead of, deleting everything so that you people don't get really confused, I won't want to confuse you at all. Let's name them with all the previous names. I'm keeping this in such a way that afterwards, if you just go through the notes, you will be able to actually figure out what happened. All right. So rather I shall copy paste it once more because that's a better option, at least in my thinking. All right, now look at the new drawing here, right? Let's forget about all this. Let's forget about this. Let's forget about this. Let's forget about this, right? And now I want to simplify this. So I have just copied one drawing more than once. Okay. All right. All right. Now say I'm just giving it different names once more. So let's call this A. If I call this A, then what is the signal that I have here? Is G2, G3A. I have G2, G3A here. If this is A, then what is the output? H1, G2A. Right? Because now this is, you can consider this one to be a new drawing altogether, right? A new entirely new system, for example. Now I'm finding the equivalent of this one. I'm finding the equivalent of this one, kind of like that, right? All right, so this was like that. Now if I pull this, so this was A, right? This was A, this was G2, G3A, and this was H1, G2A. And now instead of pulling the signal out of this, because I want to construct a feedback loop out of this, and so I cannot pull signals from here, otherwise after construction of the feedback loop, after writing down the equivalent circuit, I would have lost this internal part here. Point is that I am now pulling the signal out of this. Now what signal is coming out of this? What signal is coming out of this? Of course, G2, G3A is coming out of this. G2, G3A is coming out of this. And if G2, G3A comes out of this, what is the output of this? What is the output of this? The output is, I can see, it is a very difficult one to write actually. G2 square, G3, H1A. I have that. Very bad, really very bad, right? Do you see that? It was really very bad, right? All right, so I have G2 square, G3HA. Wow. But what I want really, I want this to be H1 G2A. I want that. So I want this transfer function to have become something such that the output here is H1 G2A, rather G2 H1A. Right? I want this transfer function to have become something such that the output is G2 H1A. So let me simplify this even further. All right, so I have G2, G3A as the input, and what output do I want? I want the output to be G2 H1A. I want the output to be, just for the sake of equivalence, right? G2 H1A. So my input is G2 G3A. My output has to be G2 H1A. So what should be the system? The system's transfer function must be the ratio of the input to the output. It's going to be G2 G3A divided by G2 H1A. You can cancel out the common terms. A can cancel out, G2 can cancel out. You essentially have G3 by H1. So you have something like this, then it's perfect now. I'm sorry, what am I saying? Output by input, right? I wrote wrong. It has to be output by input, right? Ratio has to be output by input. So G2 H1A divided by G2 G3A, right? Ratio of output to the input, of course. So A can cancel out, G2 can cancel out. I have H1 by G3. H1 by G3. Now, funny thing is that if I did choose option 2 right at the beginning, and instead of pulling this line from here to here, instead of doing that, if I pulled this line back from here, you would have straight up gotten this one, right? You would have straight up gotten this one. It's going to be H1 G2, H1 by G3, right? Absolutely. So if you had chosen option 2 right off the bat, you would have gotten this one. So we just went through a bit of trouble just to show you different things that can actually happen, right? So you have now again constructed the equivalent here. All right, nice. Now we have a nice feedback loop here. Now we have a nice feedback loop that has no external dependency whatsoever, right? Nothing is being pulled out of this. So with that said, I am going to copy it once more. All right, so now we have actually figured out the equivalence between this one and this one. Now we can actually happily get rid of all the signal representations, right? Because those were pretty much ad hoc, right? Based on what we needed, right? Right. So now we have this clean one, right? All right. So again, if you encounter any difficulty, feel free to ask. Now this is my feedback loop, right? This is the feedback loop, right? So let's construct the feedback loop. So in the feedback loop, this is the feed forward transfer function. This is like your G, right? This is the G and this is H. And if I combine this entire feedback loop into a single one, then, so to do that, let's copy and paste once more. Right? So what we are trying to do right now is we are trying to eliminate this entire feedback loop and construct a single transfer function out of this. So equivalent of the feedback loop. So we are drawing the equivalent of this feedback loop. All right. So equivalent of this feedback loop. And now what is the feed forward transfer function? It was supposed to be something like G, right? And this is like H in the feedback configuration. Let's go back to the feedback configuration, right? So this is like G and that was H, and of course for negative feedback, right? So I would have an equivalent transfer function of G by 1 plus GH. So with that said, so this is G and this is H. So after converting everything into their equivalent circuits, I would have, so instead of, so it will be G by 1 plus GH. Now G is G2 G3, so I would have G2 G3 here, and H is H2, so I would have G2 G3 H2, right? All right. Now I can happily see a cascade here. Can I see a cascade here? Yes, I can see a cascade here, right? So this is a cascade, right? This is going to be a cascade, right? So let me just copy paste once more. Oh, what did I copy? Sorry. So this is another cascade block, right? So basically this transfer function gets multiplied with this one, right? So essentially, if I remove this and write everything as a combined cascade block, right, what would I have here is G1 G2 G3 divided by 1 plus G2 G3 H2. G1 G2 G3 divided by 1 plus G2 G3 H2. So what happened is this just got multiplied with this transfer function because we have 2 in cascade, right? All right. Now we have a feedback loop. Now we have a feedback loop here. Another simple feedback loop. Now again, in the feedback loop, consider this to be G, this entire thing to be H. Okay, this entire thing is the feedback loop, this thing is the feedback loop, right? All right, so consider this to be G and this to be H. All right, so in the feedback loop, if I construct this, just a little bit of mathematics would help us, but let's construct this, or rather copy paste this one. All right, so I have just gotten rid of this entire feedback loop, right? All right, so instead I have one gigantic transfer function. All right, I have one gigantic transfer function, and now see, this is your G, this is your H, right? So of course the equivalent transfer function, let me reduce the zoom a bit, because otherwise I don't know if you can see, if you will be able to see this. So this is going to be G by 1 plus GH, but unfortunately for us they are very complicated terms, so let's get on to it, right? All right, let me try my best. So instead of G I'm going to write that, and instead of H I'm going to write that. All right, so G2, so let's do the mathematics separately, huh? Much better for me. So G is this one, and H is that one, H1 by G3. You understand what trouble I'm facing right now, right? H1 by G3. So I want to calculate this. I want to calculate equivalent transfer function, which is G by 1 plus GH. So that's going to be equal to G1, G2, G3 divided by 1 plus G2, sorry, G2, G3, H2 divided by 1 plus, as long as I can copy paste, I shall copy paste, into H1 by G3, right? Just follow along the calculation, because I am really bad at making sure my calculations are correct. So G3 cancels out actually, right? So I have G1, G2, G3 divided by 1 plus G2, G3, H2 divided by 1 plus, so I essentially have G1, G2, H1, and again we are just seeing algebra, right? Because this is block diagram algebra, right? 1 plus G2, G3, H2, right? So now I think we need to pull this to the left side. Now this is just rough calculation, right? So this is now going to be G1, G2, G3 divided by 1 plus G2, G3, H2. I'm combining this one with here, so this becomes 1 plus G2, G3, H2, and then I have 1 plus G2, G3, H2 plus G1, G2, H1. Combining these two, of course these denominators from both of them will cancel out, so I essentially have G1, G2, G3 divided by 1 plus, I promised I would copy paste as long as I can copy paste, right? So I have G1, G2, G3, and then this one, right? That's the whole thing. All right, yes. Someone saying it's very, very difficult, right? So let me just copy, paste, copy, and paste it here. Nice. So after this is the conversion we had. And this is your rough work, right? So where does the rough work go? They become pretty small like that. Like it never happened. Like we are so intelligent that we actually did this. Right off the back of our head, right? So this is rough work. Anyway. Alright, so alright. Now look at this one. Now imagine this entire system to be G. Again, these are just our simplification, assumption for simplification, right? Consider this to be G. Hold on. My water bottle is empty and I need to get some water. Yes, actually one of you is right. So on the next class, we shall talk about signal flow graphs, and signal flow graph would be one step way to get this entire thing. So you'd be able to reduce the entire block diagram into a single transfer function in a single step, right? Using signal flow graph. But that comes from the idea of graph theory, right? The problem is that while teaching you signal flow graph, I won't be able to teach you the underlying theory of that, right? I won't be able to give you a derivation of Mason's gain formula, right? Unfortunately, because your knowledge of graph theory is not sufficient for that, right? So, I mean, if I just taught you signal flow graph and told you, okay, this is the mechanism in which you actually reduce a big complicated block diagram into a single transfer function, that would have done the job, but you would never have some other tool to verify what you have got. So block diagram reduction technique is an obsolete technique. No one really uses that simply because this is so cumbersome, right? But this is still used as a tool for students to verify, to be able to make the students be able to verify what they have, what they would get otherwise by using signal flow graph. So actually, while actually teaching, I often do this thing. I take a single system and convert or simplify that using, say, a block diagram reduction technique, and then I solve that using signal flow graph, and the results should agree. We should end up with the same transfer function at the end, right? But signal flow graph is of course a more modern and a single step technique. So you have to do some calculation, but after that, using a single step, you will end up with the result. Okay, right? So that's one of the things. And of course we teach both, right? Because again, in the very first class, I told you what we are teaching you is ancient history. And when you study history, you just don't forget a certain period in history, right? You study everything. That is what is happening right now. Okay, so we are saying that this is G right now, right? This is G. But what about this single line here? Of course, if we had a transfer function like this, if we had a transfer function like h here, we could have been just happy, right? H here, fine, we have a simple feedback loop, right? But instead of this h here, we have a straight line joining that, right? So let me just draw it once more. So what we essentially have is something like a feedback loop. Look very carefully. I have a transfer function g that generates an output, and usually I do have a feedback transfer function as well, h, that takes the output and feeds it back to the input with a comparator, and this is x and this is y. So right now essentially what we have under this scenario is that y is being fed back to the input, right, directly. So this configuration where I just have a straight line like that, just a straight connection, is nothing but h being equal to 1, right? That simple configuration, this is equivalent to this configuration, right? This is equivalent to this configuration, right? Just saying this and saying this are equivalent, because at the end of the day y is the signal here and I'm multiplying y with 1, so I have y here, and here by this simple diagram I have x coming in here and y coming in here. Then again we have not violated any signal constraints anywhere, right? So this one is essentially a feedback loop where the feedback transfer function is equal to 1. Right? Right? So now, with that said, if I reduce everything, then the total block diagram becomes this, total block diagram. So we have reduced everything, right? So this entire thing is now a single feedback loop, and the forward transfer function is g and the feedback is h, but h is 1 here in this particular scenario. So now we would construct a single block, single gigantic block. Alright, single gigantic block where the input was just like that, x, and the output was just like that, y. And we said, okay, we are considering this to be g and this to be h. Of course, my transfer function is going to turn out to be g by 1 plus gh. But happily right now h is equal to 1. So right now let me write down. Now again, we are doing rough work. And then in the end, we are going to pretend like the rough work did not exist. So this is g. Let me just copy paste once more. So this is g, and for this particular scenario h is equal to 1, right? So we are calculating g by 1 plus gh, and that's gonna be this by this. So anyway, just a moment. So g by 1 plus g, right? Because h is equal to 1 here in this particular example. Now g is this one, and let me reduce this a bit, and divided by 1 plus this one. So now we have g by 1 plus g, right? All right. So let's do the simplification, and if I do the simplification, of course this is going to turn out to be in the denominator and denominators will cancel out. I can kind of write this in a single step, I think. So this is going to be g1 g2 g3 divided by this whole thing, then a plus this whole thing. All right, so successfully we have actually copy pasted everything. So copy and go back here and paste. So this is the overall transfer function of the system. And this again goes in as a footnote. So let's go back what we have done so far. We had this system, okay, right? And after so many simplification steps, we now have reduced everything or reduced the abstraction so far that we just have a single transfer function representing the entire system. We just have now a single transfer function representing the entire system. Right? So if I do one more copy paste one last time and bring the original drawing back in. I know this wasn't the original drawing. So what I essentially have is that if I have this as the system, let me just reduce this a bit. Right? This was the original system. This was the original input to the system. So this was the original input to the system and this was the original output to the system. So we have reduced this entire system, or rather entire abstraction into a single. So one is saying, which one is saying H1? Sorry, that is going to be H1, right? So we have reduced this entire block diagram into a single one where we have this input, but this entire system is going to be represented by a single block diagram. Maybe it was too big. Hold on. We have the same system, and this entire internal mechanism is going to be described by a single transfer function. The output is still going to be the same. So what we have done essentially, we have reduced the abstraction of the description. So this was still a little bit of abstraction there, right? So a little bit of lower level abstraction. So we actually were giving you how individual blocks were interacting with each other. Now here we have reduced the abstraction so far that we won't even be able to see how the individual blocks G1, G2, G3, H1, H2 interact with each other. But instead I just have an overall idea of how the entire system behaves with external input and generates outputs, right? So block diagram reduction and signal flow graph, these are two different techniques solving the same purpose of reducing the level of abstraction from our description of physical systems. So this is actually was describing a physical system with some level of abstraction built in within it, right? Because this G1 block was a controller, maybe something like that. So this had already built-in mechanisms that were simplified into a mathematical representation. This was the plant, or this was the control system. And similarly, these were sensors and all those things. We already had removed some level of abstractions. Now we have reduced the level of abstraction as far as practicable, and we have converted everything into a single block so that we only get to understand, or rather get to see, the relationship between the input, overall input, and the overall output, right? So this is one of the techniques that we people use, known as the block diagram reduction technique. But again, just to give you what should I say, just to make sure that you understand this very well, that you have to understand that we did not apply any formula per se other than the cascading series combination, a parallel combination, and the feedback combination. Everything else was derivable simply by looking at how the signals are changing, how we made sure that the signals did not change, right? Based on that, we actually derived everything. And on second thought, I think we shall continue this discussion onto the next class, and we shall solve a few more systems, and so that you have a better understanding of block diagram reduction technique. In the meantime, this would be your homework. Try solving this. So homework is also known as assignment, right? So this is going to be your homework assignment. All right. So again, just as usual, forget about those S terms. Simply forget about those S terms. Does anyone have any question? If you have any question, feel free to ask, because I won't be waiting here after the end of the discussion. All right. Right. This is X. This is Y. Then this is the feedback coming in. I can see. So this is G1. That's gonna be G2. This is going to be G3. This is going to be G4. This is going to be H1. H2. So that's going to be your homework assignment, is to find. So question would be, find the overall transfer function y by x. So just so that you know, this transfer function was simply y by x, right? So this was just y by x. Anyway, so that will be your objective, at least as a homework problem. Try doing that. With that said, this will be the end of our discussion today. I already took way too long, so don't worry, we shall continue these problems in the next class. All right, thank you for being here, and stay safe. I shall see you next week. Again, if you have any query during the week, just drop me an email. Thank you very much.